In this lecture, we will show how we can design algorithms.
Before we can present or discuss any algorithms, we first need to make an important decision. How do we represent algorithms? How do we use notations? How do we express the instructions that are involved with the algorithms? Well, one possibility is to use a natural language, the language that we speak and write on a regular basis. So like, for example, English, or maybe Spanish, or Arabic, or Japanese, or Chinese, or whatever. And this is an obvious choice just because we're familiar with these languages. We use them every day when speaking and writing. So whenever we write our algorithms, it can be structured more like a paper or an essay. But there is a major problem with using natural languages. And it's because there really isn't the organized structure that we need in an algorithm, and the text is just way too verbose. Natural languages are great if we're trying to write novels or poetry or essays because we have this unstructured, free-flowing style. But this is horrible for algorithms because, like, well, for instance, there's too much information that's left open to interpretation. If you're writing like in an essay format or writing some piece of poetry, you usually have different people who have different interpretations of that poetry, what it means to them, what their meaning is. But we can't have that for algorithms. As we mentioned before in the last lecture, we cannot let the computer guess what a particular step is. It has to be clear, it has to be concise. There can't be any ambiguity, and there is a lot of ambiguity when writing using natural languages. The other issue is it's very difficult to follow steps. You read an entire paragraph and you might have to read it a couple times, or just trying to figure out what steps we need to repeat, if we need to skip steps, where do we go, but it just becomes very difficult to read and understand as far as following a set of instructions. Here's an example of our addition algorithm that we did a while back, where we're adding two different numbers by adding the respective digits and the carry digit. So go ahead and take a minute, pause the video if you need to go ahead and read this over. Okay, does this make much sense? If we read over the whole thing, we might get an idea of what the algorithm is trying to say. But the problem is there's different parts that are very difficult to comprehend. There's too many things that are left open to interpretation. Let me give you just one example, if I can find it here. So there's a sentence here that says when you're finished with the operation, it talks about adding all the bits. And then it says right here, we're going to add 1 to I, and then begin the loop all over again. So this part right here. So it says we need to begin the loop all over again. Where did the loop start? We don't see anything here that clearly says, here's the beginning of the loop, so we need to go back to here. Without any indentations or line numberings or any highlighting or anything that gives us an idea of where this loop begins, it's really difficult and daunting and time consuming to try to figure this out. So this approach just does not work for us. Okay, so natural languages, they don't work. So let's try a different approach. Let's try just going straight to a high-level programming language. So let's just, if we're going to be writing an algorithm, if we're going to be turning this into some code, let's just go ahead and write the code for it. So for example, we can use C++ and Java. These are a couple of examples of high-level languages, and there are many more, and we'll talk about them later, but these are two of the more popular ones. So here we're just going to use the exact code that the computer needs in order to execute these steps. Would this work? Yeah, it would work, but once again, there is a problem with this, because if we're going to write the code, we have to understand that particular language. We have to focus more on the syntax, or what we call the rules of that language, instead of figuring out the algorithm itself. So our focus is more on how to write the code than how to write the algorithm. Here's an example of our addition algorithm using the Java programming language. So take a look over this for just a minute. If you need to pause the video, go ahead and do so and see if you can understand what this program is doing. Okay, does this make sense to you? Well, if you already know some Java ahead of time, you probably do. But what if you don't know Java? There are things in here that you probably have no idea what they do. So like, for example, this new scanner system.in. Do you know what that does? In Java, that allows us to handle user input, and there are functions that we use to bring in like specific types of values as input. But if you didn't know any Java, you probably wouldn't know what that means. Or what about these lines right here with the square braces? Do you know what that notation means? Maybe, maybe not. Or what about these lines right here that involve imp.nextInt? Do you have any idea what that stuff does? Once again, if you don't know Java, you probably don't know what that does. Now, maybe this part right here you can probably figure out, because here we're doing something with A and something with B and adding a carry. So this looks like that we're adding the respective the values of a particular digit. So maybe the ones digit or the tens digit and so forth. So we might be able to figure that out. But the whole point here is we're trying to figure out what this code is actually saying than what our algorithm is supposed to do. So natural languages don't work and a programming language doesn't work. So what do we do? Well, let's just take the best of both parts and put them together. And this is what we call pseudocode. And this is actually a very common approach that computer scientists use for writing algorithms. So the idea with this is we still use the English language to write statements, but we do it in a programming language format. So what we're really doing is we're getting the sentences of a natural language, but we're getting the structure and the format of a programming language. So we write our algorithm kind of like code, but we just use normal English statements, and this wouldn't actually run on a computer. I mean, this isn't any language-specific code. If you try to write this up on a computer and try to tell it to execute, it's not going to be able to do it because it's not actual code. But what's nice about this is it's simple, it's very structured, and it's very easy to read because each line would correspond to a specific step. So we can see, okay, at this step we do this action, then we go to the next line, that's the next step. If we have a loop, we can see where the loop starts, we can see where the loop ends, and we don't have to worry about any of the syntax that's used in different languages. We don't have to worry about any of the rules. We don't have to worry about being verbose, about being grammatically correct, because, I mean, we are writing sentences, but we don't really care about whether a sentence is proper English. Now, don't tell your English teachers that I said that, but when it comes to writing pseudocode, we don't care too much about it. And what's nice about using pseudocode is we can take the pseudocode, and if we understand a programming language, we can use that pseudocode and translate it into actual code that would be formatted properly for that language, and then the computer could run our program.